All right, good morning. So today we will dive into deep learning, and we'll start with a type of neural network called feed-forward neural networks. Okay? So remember logistic regression, okay? We had this way of predicting what the probability of an outcome was. So that was the model here we had. And as it turned out, this was your first neural network, okay? So it's a big word because actually it's just one neuron, but still, it's a neural network nonetheless. So why do we call that a network, okay? So it's called a network because you can break down what you're doing in a graph of operations, okay? So the first thing you should remember about neural nets is that you really should think of neural nets as a graph of operation. So on the left here you have x1 and x2, and these are your inputs, okay? So by convention here, every time I try to put a scalar as in all these boxes, okay? So x1 and x2 are, say, the two features you have associated with an observation. And then you have a number of weight parameters, so w0, w1, w2, and that feeds into a function. And this first function, I call it u1, it could be any name, and it's the linear combination of my features and the weights, okay? So this is this part here, all right? And then this feeds into another function, u2, which applies a function which is really just the logistic, the sigmoid, okay? Remember? So there's two stages. First we do the linear combination, and then we apply this sigmoid function, okay? So it's a very useful way of thinking about what you're doing. It's very close to what you would do almost like in a computer program, okay? So you'll be thinking in terms of functions, and you have these little modules, you have inputs and outputs. And in this case, they just express as a directed acyclic graph, so a DAG. Okay, so why do we call that? So we now understand why it's called a network, because it's a network of operations. So why do we call that a neural network? And the reason why it's called a neural network is because when people started to work on that, they're working on artificial intelligence and so on, they're trying to model what a biological neuron was doing. And they realized from the early results in biology, studying neurons, that actually this kind of operation is very close to what a neuron does, okay? So if I go one slide, I want to be able to come back. Sorry. So if I go back one slide up here, on the left here, it's kind of the idealized version of a neuron. So you have some, on this side here, you have what's called dendrites, and they are basically your inputs from other neurons. And then comes to a cell, and the cell will do a whole bunch of stuff, and in particular, it will kind of add all the signals together and apply some kind of thresholding operation. And then we'll send that signal back to the output, and so that will be the axon terminals, and they'll be all there, okay? So it kind of is similar to what we're doing here. Remember, logistic regression, we're doing a linear combination of your features. That's your combination of all your inputs. And then you apply some kind of nonlinear operation, okay? And then you have a bunch of outputs that come out of this system. So it's very close. Okay, so this is what we had. So a neuron, when we talk about neural networks, a neuron is really that's what it is, okay? It's a function, so this kind of simplified graph of what a neuron is. So it's a class of these little nodes, okay, that takes as an input of the first step will take a linear combination of your inputs, okay? So the same as you've seen up to now, and I will apply some function f. But the function is doesn't have to be the sigmoid, okay? So the general class of these neurons, we call that activation function, okay? So this function f that would process this linear combination of your inputs, it's called an activation function. And this is, okay, sorry for the poor display. This is the best setup I could have. But on the video, hopefully, the contrast will be okay. So you have examples of 3 functions, activation functions here. So on the top left, you have the sigmoids. Okay, so that's the one you've seen. That's the one that's used in logistic regression. You have the tangent h, which is very much like the sigmoid, just a rescaled version of it. And you have on the bottom left something called the rectified linear unit, or ReLU. And it's basically, you have 2 modes, okay? If your input is less than 0, then you kind of threshold that and just return 0, okay? So you make sure that you don't return any negative values, okay? So the value you return, so if your inputs, so if your linear combination of your inputs is negative, you just return 0. And if it's positive, you leave it intact, okay? So the formulation for that is max of 0 and z. Right, so the main point of all these activation functions is to apply some kind of non-linearity, okay? So that's very important, okay? So the function f we apply, so we do something very linear here, this weighted sum, but then we need to break that linearity. So we're going to apply some nonlinear function. And the type of nonlinear function you apply doesn't really matter fundamentally, okay? So I present here 3 activation functions, but if you look in the literature, you have many more types of functions out there, okay? So in fact, you can show that some results that say that, well, they're roughly equivalent, and let's put it this way, it'd be very hard to come to a conference and propose yet another activation function, okay? All these activation functions we have, they're just fine. You just have to pick from the pool of existing and common ones and see which one works best for you, okay? But knowing that if you have enough neurons, then it doesn't really matter what you're doing. Okay, so as I said originally, so all these works kind of were trying to mimic what nature was doing, trying to understand how this was doing. But obviously, at some point, we thought that we're just going the full engineering way on that, and we don't really care about the biology analogy, and we only care about getting the best results in terms of machine learning. Okay, so it's good to have in mind what nature does, but it's not. For what we're doing, it's not really that important. Okay. So we've seen what a neuron is. So a neuron is just these 2 parts, linear combination and non-linearity. And now we can combine all these neurons together and form a neural net. Okay? So this is a classic organization. This is called FeedForward neural nets. And so you can see on the left, you have all the inputs. It's called the first layer. Okay? And then from this first layer, it's fully connected to another layer. It's kind of an intermediate layer, and this layer will be called the hidden layer. Okay, so hidden is a bit a strange word here, but basically, any node that is not an input or output will be called a hidden layer, a hidden node, and another way of thinking about that is just an intermediate variable. Okay, so it's an intermediate results in your graph. So anyway, so on the left you have the input layer, and then you have a bunch of nodes stacked into this hidden layer, and all these nodes are fully connected to the inputs. So by fully connected, that means that every single input is connected to one of the hidden layers. Okay, and then you imagine that each of these nodes is a neuron. So it will take a linear combination of these inputs and apply some non-linearity. So say, for instance, a sigmoid. And then what we left at this point is basically you went from on the left, you had 4 inputs. And now, when you progress after the hidden layer, what you have is 5 inputs. Okay, so you have computed 5 numbers now. And so you can start from afresh and say, right, now we have 5 inputs. We're going to connect these 5 new inputs to a new layer. Okay, in this case, there will be just the output node. All right, so it's quite simple. Just think programming. You have little bricks, little code, little functions, and you just combine them in a directed acyclic graph. Okay, so that's a neural net, feedforward neural net. And if you have more than 2 hidden layers, okay, you have what's called a deep feedforward neural nets. Okay, and so at this point, you've seen all what there is to see about deep neural nets. Okay, so there's not much between a neural net and a deep neural net. You don't have to go very far. You just need to have 2 hidden layers, and you're doing already deep neural networks. Okay. So once again here, in a feedforward neural net, all the nodes are fully connected from one layer to the other layer. Okay. Now here I have one output, but you could have more than one output. Okay, you're not limited to just one output. You could have more than one output. Right. So why are we doing this? I mean, what's the reasoning? Why would it work? Okay. So the reason why it's useful and kind of very useful basis for working on machine learning is that we know from the universal approximation theorem that you can basically approximate any function by a neural net. Okay, and you don't need to go very far. A neural net this way, so with only one hidden layer, is enough. Okay. All you need to do is to add quite a lot of hidden nodes in your hidden layer. Okay, so provided you have enough of these little neurons in your hidden layer, then you can approximate as well as you want any continuous function. All right. Now this seems a bit alien. We're going to play around and show you why we mean by that and how I kind of try to make you have a feel for it. But anyway, it's a very important theorem that tells you, okay, we can approximate any function, so basically we can, do any kind of machine learning. So that's very good. Okay. But what we've seen, so the universal theorem only works with was derived for only one hidden layer. But we know from experience, like all the research papers now are going for deeper and deeper layers. Okay, so by deep means like adding more and more of these hidden layers. Okay, so if you just have one hidden layer, that's a very shallow network. If you have 2, it's still quite shallow, but it's called deep. But nowadays you'd have easily 50 or even 100 layers deep of neural networks. Okay, and the depth of this neural network is very important. And that is because, as we're going to see, basically, after each hidden layer, you create new features. Okay, so it's coming back to what we discussed about the kernel trick and SVM and so on. One of the main questions we have is how do we reuse and recombine our initial features into more interesting features? Okay, so we need to recombine our inputs into something a bit more useful that is more powerful. And these layers basically do that. Okay, they will give you more and more features, more and more complex features. And we know that the deeper we go, the better the networks are, the more efficient, the less parameters we need, and the better they generalize. So, in a way, okay, the way I like to think about it is neural nets provide you a framework. It's kind of like a little programming language with these little nodes, these little bricks, Lego bricks. And what we're doing at this point is no more trying to find new mathematical insight on something. Okay, we're just trying to architect some kind of network that would be more efficient. Okay, so if you look at the literature, there's very little discussions about maths anymore. Okay, it's all about how you organize your neurons together in a way that's more efficient for training and that gets you better, faster classification. Okay, so it's all about the architecture of the neural nets. So I already briefly mentioned that deeper is better, but there's different ways of organizing all your neurons and how you put your connections and so on. And this is where really the research is, if you want. Okay, so there is this little website on TensorFlow.org. So this is called playgroundtensorflow.org. And I definitely advise you to have a look at it. So I'll just, it's very nice little UI for you to get to understand what's going on. So on the right here, you have a data set, okay? So they propose you, if you see here, there's different kinds of data set you can apply. You can start with a simple one here. So you have two classes, the blue one at the center and the orange one at the periphery. I'm going to start and try to stick to two types of features. Okay, so you have two features, so x1 and x2. And basically what you see here is the color-coded intensity of the feature. Okay, so negative means it's positive, and orange means, blue means it's positive, and orange means it's negative. So basically, what your two features do here is it's basically the x and the y axis. Okay, so you just collect. You have observation, you have a point, and what you do is you collect what the x and y coordinates are. Okay, so this is what your x1 and x2 are. Okay, so x1 for x coordinate and x2 for y coordinate. And then we feed that, so we have this connection. So this is a fully connected network. And we have 4 neurons here, okay? So just reset that. So we have put 4 neurons, but you can add more and less, okay? So we'll just start with 4. And then I just want to have one neuron as the output, okay? So sorry, I'll just have one hidden layer. So at the end, we'll have one output here, okay, which is not presented. So the activation functions are going to be set to the tangent edge, but you can change to whatever you want. And I will leave regularization, learning rates, and so on alone, and something we'll discuss later on, okay? So I'm going to start the training, and you see that very quickly, in this case, you converge to a reasonable solution, okay? What I like about this interface, so on the top right here, what you see is the loss function going down, okay? So your loss function, remember in logistic regression, we use the gradient descent technique. Here we're using something similar. So here the loss function tells you that you converge, and that's all fine. So then you can, interestingly, here we can click on each of the neurons and see what kind of feature you have, okay? So basically what we're doing here is, we evaluate for every single point in your plane here, you evaluate the output, and whether it's positive, it would be blue. If it's negative, it would be orange. So you can see that in the first hidden layer, basically what you've done is simply found rotations of your axis, okay? And that makes sense. I mean, at the first hidden layer, what you're doing is you're doing a linear combination of your inputs, okay? So you're taking proportion of x plus a proportion of y, okay? And then you pass through the nonlinear function. But basically, that the linear part, all it does, it will rotate, do a linear transformation of your features, and a linear transformation is mainly, in this case, a rotation, okay? So you kind of rotate and maybe shear your data. So these first neurons, all they do is they propose different rotation of your coordinates and see if one is better than the other one. And then, at the end here, the last neuron will feed into these different rotated coordinates and basically reuse these features as for the final decision. Okay? So let's make that maybe simpler. If we just train with 3 neurons, you will see with 3 neurons, well, actually even less, okay. All right, so with 2, you see when there is no hidden layer, you see it's not, well, you can't see anything, but it's just not working very well, okay? You get just a straight line. If you add 1, so 1 hidden layer, so these 2 features, before we, they're just rotation of these guys, and then what we do is we combine, it's kind of like the last node, if you want, acts as an AND operation, okay? So we'll say, are you in this part of the plane? So you can see this feature here takes the lower half and the upper top, and so by we were doing here the sum of the 2 somehow, okay? We combine these 2 graphs together to have this upper part and lower part together, okay? So this is how we combine things. But you can add more neurons, okay? And as you add more neurons, basically, we are going to have more planes, and more planes will be, the last neuron is going to take the combination of all these planes, all these, and we combine them to form an intersection of those, okay? So let's see maybe a more difficult string set here. So here you have a spiral, and it's quite intricate. Like there's a narrow boundary, and it's definitely nonlinear. So if we restart the training, you will see that only with 4 neurons you're not going to go very far. Okay. Still trying to do something, but you're not going very far. Now it's important to look at the plot of the loss function here to see, if you're getting stuck or not. And you can see that you're not going down very well. So you can add more neurons, okay? And we know if we add enough neurons here, okay, from the universal theorem, we know that you can actually converge to the correct solution, okay? So you know that if you have enough neurons here, okay, it'll just be fine. So in this case, we can see it's going down, it's going down, it's going down. And we're probably not going to converge to the correct solution, okay? Now, it's something very important to keep in mind when you do neural nets, okay? The network architecture you have might be correct, okay? You might have put the right number of neurons and so on. But because you're going to fundamentally use a gradient descent algorithm, you're not guaranteed to actually converge to the optimal solution, okay? So when you train neural nets, you might spend weeks training your neural net and actually get stuck in a part of the search space which is not interesting. So you spend weeks training your algorithm and you just get stuck and you don't get a good results, okay? And that is actually a big problem in the research community right now. Is there's a lot of papers that say we have amazing results, but we don't really know if it's because of the network or because the people were very lucky that during the training actually they just converge to the very good minimum. Okay, so I just wanted to show you now what happens when you add layers. Okay, so we'll add a few more layers and see what happens. Okay. There's a bit of luck involved, right? So I mean, we don't know exactly what will happen. All right, so when you see this behavior, okay, so it's very typical, okay? So you see you're going down, and then at some point, it oscillates, okay? When you have oscillation, it's because of your learning rate. Remember the gradient descent? The learning rate is the speed at which you follow the gradient. And that's because your learning rate is too high at this point. So, sometimes you're lucky enough, you get out of this oscillation. Another way is, in this demo here, you can change the learning rate and you can go slower, for instance. If you go slower, then probably you won't see these oscillations anymore and you'll be fine. Okay, so anyway, it is possible to get just from these two initial features to get to the solution. I played a bit with that and it's in the slides, and but it took a bit of a few tries and errors. So it's not you just how you train set, press enter and just magically works. Okay, it involves a bit of luck there. But let's look for a second at what's going on. So the first layer, still the features you get are just really other lines, okay? And that's because, as I said, the only thing you're doing here is the linear combination of these two guys, and so all what you can get really is just a rotation of this boundary decision. But the second layer is more interesting. Already when you recombine these inner layers, you can do funky stuff, okay? So you can see these features are more interesting, okay? They're a bit more complex, really. And then you can recombine these features into even more complex, combination of your initial features, okay? And then the last decision is just, this combination of these two guys. So if you want conceptually, the way people think about it is like, these guys are your raw features, and then you go about doing some kind of little update or recombination of those, and they're still quite low-level features, but just slightly higher up. And then you go up and go up and go up, and at the end you have something very meaningful, almost something like a human could interpret. Okay, so you kind of go up and up, and the last layers are kind of almost like semantic level. Okay. This will become even more visual when we look at convolutional neural nets, when we work on pictures. Okay, so that would become even more obvious. All right, so definitely play with that. That will help you understand what's going on. That will help you understand as well why the universal theorem works. Okay, and so definitely play. You should play with that. Okay, so this is what I said. So just on the slides. Somehow managed to get miraculously to a correct combination of, but anyway, it was luck. Okay, so that's the output of your inputs. First layer, second layer, third layer, and at this point you're ready to go for the last stage. Okay, so. Let's talk about training, okay? So there's two things going on, okay? There's what's called the evaluation network and the training network. So let's take this example of a network, okay? So we have, if you want, two hidden layers and one output here. And each of the hidden layers depends on, so the first one depends on the inputs. So you have 3 inputs and on some parameters here. So in green, you have the inputs, and the parameters are in yellow, and the output is these guys. To reinforce the fact that it's really just a graph, I've decided to rename all the nodes as just being U and indexed by number. Okay, and I call it U because instead of calling node, we call that units. Okay, so I won't use the word node anymore. I will just use the word units. Okay, so unit of computation, if you want. Okay, so each of the units, okay, so form nodes of your graph. Okay, so I said that I don't care really what's going on. I just say the output of each unit would be U indexed by the index of your unit. Okay, so U7 would be the output of that particular unit. All right. So when we evaluate this graph, okay, we get the outputs, and in this case, we produce 3 outputs. Okay, so we have 3 numbers as a result of that function. Now, if we do training, we are going to combine. We need to a loss function. Okay, so remember training. The output of the training is a loss function, just a scalar. So what we need to do is to connect all the outputs to this little box, this little unit that evaluates what the loss function is. Just remember what's going on. The loss function usually, if you remember, like if you look at the cross entropy, but even in this square, it's usually the sum of over all your observation of some distance between your prediction, so the function of your inputs and weights, and what you should get, so the vector of your observations. Okay? So you have your prediction, your f, this is part, and you have the output here, and you have a little function that tells you how far you are. Okay? So depending on whether you have cross entropy or other error functions, this little function e will change. Okay, but basically we know it's a function of that. Okay, and we can do that for every single observation. So say it again. So this is kind of here we evaluate the contribution of an observation to the loss function. Okay, so we have the inputs, and the inputs corresponds to one observation, and we evaluate the entire graph, and at the end we have E, and E is the error that you have for that particular observation. Okay, so E is the the misclassification, or it's the distance to whatever. Okay, makes sense. Okay, so evaluation graph, you stop short here. You just when you run your application on your mobile phone or somewhere, this is what you have. But for the training, you need to add this, you need to connect your outputs to something, to a last layer. Okay, and this last node is this loss function. Okay, so basically at the core of the optimization of the training, you'll have a gradient descent approach. Now we'll see in the part 2 of this lecture material that actually there is different types of strategy of gradient descent, but there are just variation on that particular equation. Okay, so you first need to look at where the gradient, what the gradient is, and then go again that direction. So the problem is, how do you compute the gradients of your loss against any parameter? Okay, so remember, going back at your graph, what you want to see is this is my output, and these are my parameters. And you want to know if I vary one of the parameters, say U4 here. So if I change slightly U4, what is the impact on the loss function? Okay, you cannot change the input that's given by your, this is your training set. Okay, the only thing you can change in your training is these parameters. Okay, these are your, the weights you have. So what you want to know is like, okay, if I move one of the parameters, how it will affect the loss function? And obviously we want to move the parameters in such a way that the loss function will decrease. Okay, we want to minimize that error E. Okay, is that clear? All following? So the whole question is how do we compute that gradient? And that is the subject of backpropagation. Okay, so before backpropagation, so 1986, we didn't really have a good solution for that, and basically neural nets were just not practical. And the reason why having an efficient algorithm is so important is look at what we could do. Okay, by definition, the gradient is something like that. Okay, if you look at the gradient of your loss against one of the parameters, basically you're looking at you could do a finite difference approximation. So you evaluate your network twice, one for your the parameter at wi, and one for you increase by a little number, by epsilon, okay? And you do the difference between the two outputs, okay? So you change your parameter a tiny bit, see how it changes, and then you just do you divide the difference by how much you changed, okay? So that's the definition of your differentiations, okay? So you could do that. You could say, right, I have my network, I just change each of my parameters by a tiny bit, and I see how it changes, and then I got my, relatively good approximation of my gradients. The problem is very easily, okay, you have millions of parameters, okay? You don't have to go to do crazy things in your neural nets. You see how easy it was to just add neurons, okay? And we know with loads of neurons you do better, so very easily you have millions of neurons. So now all of a sudden, that means like you have maybe 100 million of these little parameters to tune. So it means that if you want to compute the gradients, you need to do at least 100 million evaluations of your network. Okay, so you need to have your data and change the parameters 100 million times, and you record that, and then you get your gradients of 100 million values. And that's not very efficient, because remember, you have maybe billions of data in your training set, so all that put together, it's very, very slow. Okay? Backpropagation will allow you to avoid that. Okay? So it's way more efficient, and basically, all what you'll have to do is you're going to have two passes. You're going to do a forward pass where you evaluate your network, and then you're going to do a backward pass where you kind of propagate back the information from your gradients. Okay? So it's very, very, very efficient. Okay. I don't think realistically we have enough time to go through backpropagation here. I'm just going to say that it has to do with the chain rule. Okay? So just go through the chain rule, and then we'll see backpropagation next week. Remember chain rule, okay? So chain rule is a way of being able to compute the differentiates functions of functions, okay? So when you combine your functions, okay? It's very much related to our problem here, because basically in your neural nets, you apply a function on a function on top of a function on top of a function, okay? And the problem we have, say, in 1D is, let's say this is your first node, okay? So y equals g of x would be your first layer, for instance. And then after that, you have a second layer, which would be z is apply another function to the output of the first node or the first unit. Okay, so that's the first step, and then you apply that, plug that into the second step. And the question you have is, how does a variation? How do you skip the nodes? Okay, how do you that the input x has an influence on z? Okay, and to do that, well, you can combine. You can do this little trick. You say that dz over dy times dy over dx is your solution, and that's because you can divide these little small variations. Okay, so it's a convenience trick, and you've done that in the past. The problem you have, where things get a bit more complicated, is here we don't just have like a node only depends on one node. Okay, a node can depend on multiple nodes. Okay, so you more have a configuration like that where this you have x and you have your if you want your hidden layers. Okay, so the hidden layers will be your uk. So you have n of those. And they all apply some kind of function on the input x. And then you're going to recombine all these hidden layers into one single output. Okay, so you have z is a function of your hidden layers, and your hidden layers themselves are functions of your inputs. And the question you have then now is like, how does the variation of the input impacts the final result z? And what the chain rule tells you that you have this relationship, okay? So you have to combine you have to look at basically you have to sum the contribution for every single of your dependencies. Okay, so V depends on U1 and UN to UN. Okay, so it depends on n variables. So to look at the variations of Z, you have to look at the combined effect of all the variations for all these dependencies. Okay, so you really have to think of terms of dependencies. Okay, Z depends on U1 and UN. So therefore, when you look at the variations of Z, I should look at the variations of the combined contributions of all the variations from U1 to UN. Okay, so that's what the chain rule does. So I'll just go through the exercise and stop here, but I advise you to do that at work in the tutorials. Later on, after reading week, we'll look into more of those, okay? So, kind of toy example, so your change notations just to confuse you. But anyway, okay, so you have T and R are your kind of inputs, and you recombine T and R as X and Y, okay? So basically using polar coordinates, okay? So I'm going for polar coordinates to Euclidean coordinates, okay? So going from R and T to X and Y. And then my last metric would be X squared plus Y squared, okay? And then I'm looking at, what the, can I theoretically differentiate U against R? And the answer is yes. But you just have to make sure that you look at the dependencies. And you see that U depends on X and Y. So therefore, you have to have the contribution for X here and the contribution for Y here. Okay, so you need to have both. And then after, it's just a matter of applying differentiation rules, and then you're good to go and you find the correct answer. Okay? So that's the chain rule for you, okay? So that's kind of, the chain rule is, there's different variations, but that's as much as we need to know about the chain rule. So how the chain rule will help us? Yeah. So the chain rule will help us because, okay, when we start, let's say we're going to come back, we're going to propagate back the information. So you have the loss function here, and at this point, okay, so we had the forward pass, so we know what the output, all the values of all these units are. Okay, so we know that. And then the question we have, what kind of partial derivatives what can we compute? I mean, what kind of gradients can we compute? The ones, these guys, so the differentiation, the gradient of E with respect to U14, U13, and U12, which are theoretically connected to E, we can do that. And the reason we can do that is because we know that E is it's a function of these values, okay? And that's something we define ourselves, okay? So if you're looking at a least square kind of type of loss function, we define that. We say, okay, E is, we have three outputs, U12, U13, U14 are my outputs. And I just compare, I do the L2 distance, or the squared distances, okay, sum of squared distances between my outputs and some predefined values. So these ones are A, B, and C. So if you're there, your targets, your observations, okay, the results you should get. So that's a very reasonable output, okay, definition for your loss function. But you can see here, okay, it's easy to compute the partial, to differentiate according to each of the variables. It's just simple differentiation of your function as you define it, okay? So there's nothing really fancy here. That's something you can compute. The problem is when you go deeper in the network, okay? So when you have U10, how do you go about finding what the variations of E with respect to U10? And this is where the chain rules will apply, okay? Basically, what are the variables that depend on U10? Well, they're all your outputs. They are U14, U13, U12. All these variables depend on U10. And if you think of it this way, okay, that all these variables depend on U10, then you can apply the chain rules and same with the same expression we had before. And you realize, well, some things happen. So in this case, this is what we get, okay? So this exact expression for that particular network. So you see you have the contribution of U14, contribution then of U13, and contribution of U12. And what you see here is like, it's interesting because at that point, we know how to do these terms, okay? These partial differentiations, we know how to do them. Okay, we just done them before at the previous stage, okay? So all we're left to do is these guys here. And these guys, kind of the same way we derive the gradient for these three outputs. Here it's the same. U10 is a direct input of U12, so by just differentiating what the definition of U12 is, we can actually get these partial differentiations. Okay? So, for instance, okay, if you say that U14, so U14 is this guy here. Okay? So U14 is a function of U20, so U11, U10, U9, and of a parameter U5. And you know, arbitrary picked up this function. Okay, that's something that you decide on. Okay, and well then, you know, the partial derivative of U14 in respect to U10. When you look at in terms of U10, there is only one, and the coefficient is 0.2, so that's 0.2. Okay. So at this point, you realize, okay, we have all the ingredients. We know how, you know, the partial derivative of the output nodes are, and we know how to construct these other guys, the links between U10 and all these outputs of U10. And so we're good to go. You can actually simply, by applying this equation, compute what the gradient of E according to U10 is. Okay. So we only need two things. We only need to know how to compute, to evaluate the values of these guys, so what the value of U10 and so on. And we need to know how to differentiate any of these functions. So remember, these guys are functions of their inputs, and we just need to know how to differentiate this function according to any of these inputs. And as long as you know how to do that, then you have this very simple mechanism to compute any of the gradients along the way. So here we've seen how to see U10, but then you can look at U9, and you realize that U9 is connected to points, to units, for which we've already done the work, so we can actually compute the gradient for U9. And we can move on to U11, and sure enough, at some point with U5. So U5, you see the expression is a bit longer because it's connected to more points, to more units, okay? So U5 is connected to a lot more units, so you have a lot more components. But still a reasonably simple mechanism for doing that, because each of the terms here can be computed from differentiating known functions. So anyway, you can go like this, and you can propagate back into your graph, and sure enough, at some point, you found all the gradients for all the parameters, and you're good to go. But the good thing here is like you only visit every single node once, basically. Okay? So the complexity, well, the complexity is a bit funny thing. In theory, it's an order of the number of units squared, but in practice, because of the architecture of you have, because it's not fully connected, usually you just have an order of the number of units. Okay? So it's much faster. Okay, so you're able to compute the gradient in a just, you know, roughly the same time as you evaluated the network. All right. So it's important to realize that backpropagation is really the key. It's really the backbone of training neural nets. Okay, and that is probably the last piece of maths you have in neural nets. I mean, that's as far as it goes, you know, mathematics goes almost. Okay. After that, it's just network architectures and how we put together network in a smart way. but you don't have much more maths than that. That's kind of it. All right? Thank you.